Okay. So now we start with and move forward and we go towards Monte Carlo simulation. So today we have my colleague Professor Ashok Das Mahapatra. So he joined in 2009 IIT Guwahati and his research interest are primarily Monte Carlo simulation. Other than that, he also has his interest in complex fluids and in phase transition in polymeric systems, and self-assembly in block copolymers, biophysics, graphene-based nanomaterials, solar cells, and conductive hydrogels. So with this, I again extend a warm welcome to my colleague, Professor Mahapatra, and sorry, Das Mahapatra,
Yeah.
And I wish this particular lecture will give an introduction to those who are not aware with Monte Carlo. Anybody there with Monte Carlo? Okay, so I think
No.
we will be learning it from scratch. Okay.
No one.
Okay,
And
fine then. So I can then we can start the lecture
Okay.
and I welcome again.
Thank you, Domal. Then it's a tough task for me. Nobody knows what is Monte Carlo is. And they learn so many things. It may again go beyond their understanding of the. I don't know. Let me start and see. Whenever you feel uncomfortable, raise your hand, stop me, and ask this. Okay. So this is introduction. So many things are written on the slide. May not be advisable to read everything. I will try to take you through the slides. The first line is stochastic simulation method, which is Monte Carlo. So I'm not going to start Monte Carlo simulation right now. So first couple of slides will be Monte Carlo method. Then there will be a couple of slides on Monte Carlo integration. Okay. Then there will be some slides, beginning slides for the simulation as a whole. Then I will go to the Monte Carlo simulation. Okay. This is the scheme that we have. Okay. So it shows that it is a stochastic means probability, basically. Right? I think everybody is familiar of probability, right? So having some event out of many, one event out of many possibilities. That is a simple way to narrate or describe what is probability. So if any event which is driven by this kind of probability, that is grossly called as stochastic process or stochastic method. Right? Contrary, molecular dynamics is a deterministic method. I think you have learned MD after this. Okay. Okay. So the reason for this is MD starts and solely depend on Newtonian dynamics. Right? There is a particular equation. Ax dt is equal to something. If you solve the equation, you can get x versus time. So you can predict the position versus time. At any time, you can predict the properties. That is the reason it is known as deterministic. But Monte Carlo, it is something different. So one example I have given here, tossing a coin. How many probabilities are there? 8 and 10 or something else? Only 2. What about circumference? No. It's a possibility. We ignore that. You take a 5 rupees coin. It is enough thickness to stand. Right? So there is a possibility. It may be 1 out of 1,000, 1 out of million. But that possibility is non-zero. But we usually ignore that. Right? 8 and 10. Okay, so 50-50. So if you trial by say 10 times toss, is there any guarantee that you will get 5 times 8, 5 times 10? Then this is violating this rule. If I say probability 0.5, and if I say number of trials is n, then probability of head will be n into probability of head. 10 into 0.505. But in practice, you do not get that, isn't it? The reason is here. This probability that is shown 0.5, 0.5, if the number of trials tends to infinity, then this will be applicable. That means if you try keep on tossing infinite times or at least large enough time, then you may expect 50%. Right? So if you toss 1,000 times, unlikely you will get 500, 500. There will be 1 or 2 out. If you try 10,000, not exactly 5,000, maybe 1 or 2 less or more. Okay. This is what happens in finite system. And I think you studied something on molecular simulation till now. Everything is dealt with finite system, right? Not infinite. Okay. This is one example to demonstrate or prove that MC method is a decision making tool. And this slide perhaps will serve the purpose of essence of entire Monte Carlo method, entire Monte Carlo simulation. This is the backbone. Okay. I try to give you an example here. Maybe visiting a playground has a probability 70% and coming to this class, either Karyasala or any other class, usually less probability compared to anything else, right? So I have, even if I take 50-50 also doesn't matter, logic will be same. In a particular day, how we are going to take the decision? Whether you are going to playground or we are going to the classroom. On which basis you want to make the decision? Now you can say that it is my wish. I can go anywhere. But that is personal level, it is maybe correct. Scientifically, it is wrong. On which basis you are taking the decision? Okay. So to resolve this case, you need to take the help of a reference number which should be unbiased. Okay. That unbiased number is random number. Are you familiar with these random numbers? Anybody? No one. I think everybody is using calculator. Have you seen that button for random numbers? Anybody? RND or something is there, right? You press that button. Every time you press, you will get a new number. And the number is less than 1. More than 0, then less than 1. So the range is 0 to 1. And the probability also range is 0 to 1. So I have got some sort of matching range. And since it is random, assume that it is unbiased, because the random means the arrival of numbers is not pre-decided. So bottom of the slide, you can see the sequence of numbers here. Is it random or sequential? It follows a particular trend, particular pattern, right? So this number is this plus 1. I can have a progression. What about this one? That won't follow any particular trend, right? Next time, if I pick up any number beyond 10, I don't know what is coming up, right? That means picking up any number is equally probable. There is no prefixed criteria. That set is random and can be taken as unbiased. So now, if I take the help of this random number, which is uniformly distributed between 0 and 1, unbiased, and I can take the decision over it. Right? What I will do, I will pick up a number. If it is within this range, 0 to 0.7, that means 70% probability, I will go with this one. If it is not, I will go with this. In that case, if I am making a decision based on this method, I have a logic to defend myself. That I am not taking my decision by my own, not by personal will. I am taking the help of a unbiased number and making the decision. And every day I can do that. Right? Every day I will, at the morning, I will take a random number. If it is here, I will go playground. If it is here, I will go to the classroom. So every time my decision can be changing. Sometimes playground, sometimes classroom. Right? So the decision is not biased by my personal will. It is based on a particular reference number which is unbiased. Is clear? Okay. So this is the heart of all Monte Carlo method, all Monte Carlo simulation. Okay. What you need to do is, for your scientific calculation, you need to find out this probability. Okay. An entire effort will go to that finding probability of that particular process. Then to take the decision whether this process is feasible or not, you generate a random number and take the decision. Okay, I'll come back after a couple of slides again to this issue. Any questions or clarification here? Okay. So this is the basics of Monte Carlo that I have mentioned. Then this is Monte Carlo integration. I did not write that particular term, Monte Carlo integration. You learn integration by various methods. Then you name any one or two. Integration, integrating a function. What are the methods? Now, numerical, analytical methods are that. The first to start is analytical method. When analytical method fails, Then you go to the numerical method, graphical method, many other methods, right? This is one such method. I can use Monte Carlo method to integrate a function which may not be possible even by numerical method, standard numerical method. Okay. So one example is to calculate the value of pi. This is the starting problem which we start with Monte Carlo simulation in almost every practice. Okay. So here I have picture a square and a circle inscribed in red. The radius of the circle is r, so the size of this square is twice of r. So I can write this equation: area of the circle, area of the square, take the ratio of them, you get an expression for pi, which is 4 times AC by AS. This question is correct? Now, if I pick up a point somewhere here, point means coordinates, x, y, how do I know that this point is inside the circle or outside the circle? That is given by this criteria, which is equation of a circle. Right? You pick up any point x, y, put it here. A and B is the coordinates of the center of the circle. Equation is correct? Okay. Now, if keep on picking up points across this square and circle, and if the number of such points are quite large, can I write this approximate relation? This NC is the number of points within the circle. NS is the total points in the square. So I will go back once. NS will be higher than NC. Correct? So those points which are within the circle, they are also part of the square. Okay? So can I now write down this equation? It's not exactly equal. I have put an approximate sign. Okay, so I'm not equating NC is equal to AC. I'm not equating NS is equal to AS, but I'm taking the ratio. And this is only applicable if you go very large number. That I'll show after a couple of maybe next slide. When I actually calculate pi as a function of this NS, then we'll see that if you go beyond a certain number, you get the actual value of pi. Otherwise, you never get. Okay, so now during simulation, what I can do is to calculate this ratio NC by NS. I can randomly pick up the points from this x-axis from this to this range. I will define the range. Then y, I will define this range. I randomly pick up points here and pick up points here. Get an x and y. I check here. If it is satisfying, I will say this point is in the circle. So this NC, that parameter that I have shown, will be incremented by 1 once this condition is satisfied. Then at the end of generation of a large number of points, I got the value of NC, and I decided at the beginning how many points I will generate. So I have NS already with me. If I get the ratio of these two, I can calculate pi. Clear? Logic is clear? This is the simple pseudo code that I have written here. Okay. This is you have to first define total number of points. How many points you want to generate? Total. This NT and this NS is essentially same. Okay. Why it's essentially same is I can define my coordinate over here 0, 0. Right. So I decide this is my lower limit of x-axis, upper limit of x-axis. This is essentially the size of the square. Okay. So NS and NT are same. Then you define the radius of the circle, size of the square, center of the square, and then initiate. This part is clear perhaps. Any variable in programming is an additive variable. It has to be initialized to 0. If it is multiplicative, it has to be initialized to 1. I think most of the programming language follow this protocol. Right? Okay. So then your loop starts here that you want to generate 10 to the power 5 number of points. Then this NT is 10 to the power 5. You will do a for loop or any other such kind of loop. Or can you do while many things are there. And then generate a random point x and y. That means you have to 2 times you have to generate 1 for each coordinate x and y. Put it over here. Check whether this is satisfying or not. If it's satisfying, then the NC will be incremented by 1 and your loop ends. Once this loop ends, you have the value of NC. You can calculate 4 times NC by NS, get the value. And the typical trend is shown over here. Okay, so at very low value of NS or NT, total number of random numbers, this value is no longer 3.14. It is much above, or it can come below also. Repeat the simulation, you will get something different. Sometimes it become 0.5 also. Okay, but if you keep on increasing the number, this line I have not shown here, this is almost 3.14, then remaining numbers keep on matching. We keep on increasing this total numbers one after another, the 3.1423, whatever these numbers. We keep on increasing this number, maybe order of magnitude, you'll get the accuracy beyond the points. Okay, clear. So this also satisfy or answer these questions that assumptions I have taken over here. Clear? If the number of generated points is quite large, then this is applicable. Otherwise, it is not. And that is verified by this trend over here. If it is small in numbers, you will never get even 3.14. 3 will it will come below 3. Sometimes will more than 3, 5, 6 also will come. Hence it is random. Nothing is pre-decided, prefix. Clear up to this point? Okay, so let's highlight or clarify few things here. Typically random numbers are 0 to 1. Right? Now if I need a number which is not in 0 to 1, so I can decide my the range from 0 to 10, the size of the square, or I put origin in the center of the circle. In that case, it will be minus some value to plus some value. So how I am going to use this random number to manipulate and to satisfy the requirement that I have? Here it is. If it is say 0 to 10, just multiply this number into random number, the range will automatically be expanded. Okay. If it is negative to positive or some low limit to high limit, upper limit, lower limit, then you can use this equation where A is the lower limit, B is the upper limit. You can verify whether this equation is correct or not. So what is the lower limit of random number? 0. So I put 0, this part goes to 0, x equal to A. So I get lower limit. What is the upper limit of random number? 1. If I put over here B minus A remains B minus A. So A plus B minus A cancels, you have B. You get the upper limit. So equation is satisfied. So whenever you have a range of numbers which are not only 0 to 1, something different, then you can use any of these protocols to get the number. Okay. This is a general integration method. Okay. What I have shown for pi is a special application. Okay. But this method shows the general protocol. I'll go quickly. So any function if I have fx dx within the range a to b, you plot it, and this is the range of x-axis a to b. You can generate random numbers now. You already learned how to manipulate the range of random numbers from upper limit to lower limit. And this is the y-axis which presents the value of x as a function of fx as a function of x. I can plot it. Let's say this is the functional form. Okay. What is the maximum value of this fx? At which value of x? You can find out. How can you get that? Max value of any function? One is ddx, dfx, dx equal to 0. You can get the value. Other approach is you just plot it and see graphically. Okay. Let us say this is the max value. So now I have the max value of across x-axis, max value across y-axis. So I can close this square or rectangular shape. I can now go back the same protocol as I used in the pi calculation. Okay. What is area? Is basically integration is basically area under this curve. Right. So now if I assume that this is a small distorted triangle and this is a, let's say, square, right? Then if I generate now random numbers, area will represent by this much out of this much, right? So fraction of this to this overall, similar to NC by NS in the previous example. Okay. So now my job is generate random numbers across x-axis and across y-axis. I will get a point x and y. It may be here, it may be here. Right? How do I check whether the point is here or outside? In the previous case, I have used equation of the circle. Right? What should I use here? How do I know that point is below this curve or above this curve? Only those points will be counted if it is below this curve, because integration is basically area under this curve, not above. So only those points we need to consider, those who are coming below this line. How do I know this? Value of the function. Value of the function. Right. What you need to do is you get one more y. So one y you have get a based on unknown value. You get somewhere here. One y you can easily get from the same x. You put back in the fx, you can get y. The function form is not. Are you getting the point? You get x on the same x value, you get y from the function. Right? Y is equal to x. That will fall under this line, this curve. And one y you are getting randomly. So now we have two y. One y you are getting randomly, second y from the function. Now you can compare. If the randomly generated value within this range, then it is considered as a part of this area. If it is above that, we discuss. It's clear now? Same comparison, similar comparison. You complete that, and finally you can calculate the area. This is the ratio that you are getting. Int versus int by nt, essentially the number of points you accumulated over here to the total number of points that you have generated. Okay, and then b minus a into f max is the total area that you have. So this represent is the fractional of the area. This is the total area that you have. B minus A in the x-axis range, f max is the y-axis range. Assuming y starts from 0. If it is not from 0, you need to correct. Okay, so if I do that, you can calculate the interval. Clear? General procedure you can apply to many cases. If you want, you can apply this complicated equation. Are you familiar with this equation? Anybody? The second variable coefficient is coming from statistical mechanics. Quite complicated, but not so complicated. Appear to be complicated. Okay. So this UR is nothing but this potential energy function. You can choose either LG or any other potential energy function. Use this constant and you can easily integrate. The only problem will be the range is 0 to infinity. Can you really integrate? Not possible, right? What to do? Break the limit. How to break? A to infinity. The same infinity is still there, no? You can do 0 to A to B, B to C, Y to Z, Z to infinity. But still infinity remains. Right? So what to do? You might have learned somewhere. Not change the limit. You cut the limit. Infinity को काट के छोटा करना. Right? So you have to bring infinity to finite. Because in a finite system, infinity makes no sense. Isn't it? And this potential function, the moment you plot UR versus R, you will see after a certain distance it goes almost to 0. Less contribution. So put a cutoff radius, cutoff distance. Beyond which I don't want to consider. Then most of the molecular simulation will do that. They have cutoff distance. So no need to take up to infinity. So replace this infinity by R cut, cutoff distance. What should be R cut, that you need to decide. Okay, that means you have to plot UR versus R and see at which R this UR is going to almost negative. Put a finite cutoff value over there, then put a clear. Okay, then you can calculate second virial coefficient. It is quite, it gives correct value. You can check it. Provided if you have these constant values for a particular gas or any material, you can get accurate value from Monte Carlo models. Okay. Any questions or query up to this point? No. Okay, this is another example of very more complicated functions. That was straightforward function LJ, applicable for entire range. But if you look at it, there is different applicability, different value at different R value. That also you can do. And this is the way you can split entire integration into 3 different parts. Okay. So in this type of case, before you get into the programming, try to simplify numerically or analytically if possible. Then put back to the. Okay. So briefly, random number generator. Otherwise, if I do not understand this, then Monte Carlo simulation will be a little bit difficult. Okay. So there are two properties of random numbers. What I have shown 0 to 1. In some programming language, perhaps C, I don't know the updated version, it generates a number which is integer, not 0 to 1, not fraction. Then you have to divide that integer value by rand max, maximum random number. That is predefined within the code. So you have to first get the rand max value, then generate a random number which is integer, divide, you will get fractional value. Okay. In some other programming language, it is inbuilt. The moment you give the command, it will give 0 to 1 value. Okay. So you can check the distribution of random numbers. We have claimed that it is 0 to 1 uniformly distributed. How do I check that? So you can do this checking. You keep on generating from 0 to 1. You know how to bin different numbers. You might have learned that 0 to 0.1, 0.1 to 0.2, 0.2 to 0.3 like this. So generate numbers in these zones, segregate them and plot. Plot as a histogram. If the histogram looks like this, then the random numbers is okay. If it's looking like this, then it is not okay. Of course, it depends on how many numbers you have generated. If you generate only 10, 100 numbers, you will get much worse picture over here. But you generate 10 to the 5 or 10 to the 6 numbers, you may expect quite nice plot. That gives that an impression that okay, whatever random numbers we are using, it is uniformly distributed, means every number has almost equal probability to pick up. That is the mean. That is also gives that justification that the number is unbiased. Okay. Either you can write your own code for random numbers, otherwise you can use which exists. But in most of the cases, you have to initialize the random numbers. Okay. And in that case, the initialization takes place with a numerical value or integer value. This is called seed number. Across that, you can generate random numbers. Now, every time either you need to change the seed number or make something automatically, it takes the number. So what I use is the CPU time. This I don't know whether I have it. I do not have it here. Let me see. Here it is. Random number generator seed number. That I use random number generator time null. Those who are familiar with programming, I think you can easily know what is the outcome of time null. What is the outcome? Current time. This is maybe for C, C++ programming. And other language, similar protocols must be there. Okay. And this time null or current time is changing every time. So you do not need to change the seed number every time that you want. Okay. Okay. So this is little bit of random numbers. Let's move to the sampling and metropolis Monte Carlo. Going little bit closer to the Monte Carlo simulation. What is sampling? Picking up the points or energy states, something like this. So when you go to any vegetable shop or food shop, what is the mechanism that you follow to buy a dozen of food? You follow some sort of sampling, knowingly or unknowingly, right? You do that sampling, right? You pick up, you check whether it is okay or not. If it is not, you put it back. Then try something else. Similar to sampling, isn't it? Okay. So, and typical energy distribution curve looks like this. Familiar? This is under which condition? Under which condition you may expect this kind of energy distribution? Okay, I'm giving two options. You can easily pick up the correct one. If the system is under equilibrium or non-equilibrium. Okay. So if the system is under thermal equilibrium or mechanical equilibrium, you may expect this kind of curve. If it is not, curve will be distorted, either towards this or any other shape it can. Okay, so just quickly go through the probability, which may be relevant for the next couple of slides. This is known. First one, conditional probability, right? Px of y, probability of x given the value of y. And second concept that will be needed here, if I have a series of events which has probability P1, P2, P3, what is the overall probability? That is not summation of probability, is the multiplication or product of all the probabilities that is given. This may be relevant in the next to next. Okay. Now let's start with the Markov's process. Anybody is familiar with this? No one? Okay. So Markov process states that if you have a sequential event from 1 to 6 or even 10, then this outcome of this may depend on the outcome of the previous. For example, suppose you had a heavy dinner yesterday. What is the probability that you will have heavy breakfast today? Very less. If you have a heavy lunch today, what is the probability that you will have a heavy dinner to the night? Less. So it says that outcome of this process may be influenced by the previous one. Okay. If it is influenced by only the first one, previous that is first order Markov process. If it is influenced by more than one, maybe let's say outcome of this 4 is depend on 3, 2, and 1. Then I will say it is the third order Markov process. Okay. If it is independent, outcome is independent. It does not depend on any of the previous. Then that is zeroth order Markov process. Typically, tea break is independent. Whether you have heavy lunch or breakfast doesn't matter. You go for it. Right? Tossing of a coin that I have started with. Which order Markov process it can have? Zeroth order. Does not depend, right? First tossing may be head. Second trial, does it depend on the outcome of the first one? No. So there are so many events are there which falls under zeroth order, and so many processes which may be first order, second order, third order, and so on. Okay. So this Metropolis Monte Carlo that we will be using heavily in the Monte Carlo simulator may be first order Markov. So you need to understand that before you go to get into that. This is one example I have shown how to use them. What is the meaning of this? So this is some sort of weather forecasting, rain, no rain business. This is a typical probability I have shown. If today 0.6% or 60% probability of rain, then 40% no rain, and this is tomorrow. This matrix, the way it is framed, is considered to be invariant. Means it is almost a standard protocol. This is applicable today, tomorrow, and here. That is known as transition matrix. Then if I multiply it by this transition matrix with the today's actual probability, I will get tomorrow's probability. So this matrix remains invariant, at least so far as this kind of problem is concerned. Now we can change this matrix provided you have updated value of this in certain other circumstances. Otherwise, this will remain constant. Okay. In many such processes, you may need to calculate or evaluate this matrix for that particular process, and then multiply probability one after another. You can get probability for the next day or next day. Now, if I do that, keep on multiplying this, finally I can get this kind of equation. The probability of this rain or no rain for nth day can actually be shown as probability of 0th day multiplied by pi ij, which is the transition matrix, to the power n. If you are not convinced, you can do this calculation by your own. You can check it. This is the 0th day. this 0.5, 0.5, P0. This is actually P1 and this is P2. If you want to get from this to this directly, square it, you will get it here. Okay, you can cross check this. And this concept is used in Metropolis Monte Carlo as well. Okay, how much time I have? Can I go through this? Okay, I'm not going to move all the details, but quickly I will take the slide so that you understand the application of first order macro process and zeroth order macro. I don't know how many of you have polymer background, but at least theoretical polymerization that you have done in 12th chemistry. This much is more than sufficient. Okay, so I have a copolymer where I have two different types of epitopes, maybe ethylene, propylene. These are known names, right? Ethylene, propylene. Assume that A is ethylene, B is propylene. So I have ethylene, propylene, copolymer. So I have four possibilities here. This is only the propagation step, assuming that initialization already over. Then I have this all possibilities I have tabulated over here. If the terminal limit is A, it can react with A, it can react with B. So I have A and A B. If it is B, then I have two other possibilities. So I have all combiningly four such possibilities. Now I have to simulate this process to generate a sequence of copolymer with a certain number of B in this something like this. This is not random, bottom one. You can calculate number of A in between B, perhaps you will find it is same. Some sort of blockiness. Okay. The first one is random sequence. I have to generate this kind of sequence using Monte Carlo. Then how to proceed? Its objective is clear. Okay. So I have to use these four different possibilities, right? Then I have to calculate probability of each of these steps. Okay. Then I can use the random numbers and I can proceed further. Okay. So I will skip all these things and get back to the probability equation. Let me. Okay. So if I want to calculate probability of this step, what should be the expression for this? Rate of this divided by rate of this plus this. Correct? Because this has two possibilities. So if I want to calculate probability of this part, AA, then rate of this divided by total rates. Clear? This is exactly what we have done somewhere down the line. Yeah. Probability of AA, to solve it, you get an equation something like this. RA is the reactivity ratio of A that I have defined previously. The rate constant of A to rate constant of AB, that is the reactivity ratio of A. This is the activity ratio of B, and this is the feed mole ratio. How much A and how much B you have supplied to the reactor. Okay, so using this, assuming that these values are known to you, then you can calculate this probability from this expression. Okay, then for PAB, you can get an expression and all four A. Okay, so all four probabilities you have in your hands. Now I can construct that transition matrix that I have mentioned 1 or 2 slides back, something like this. Okay, I have four probabilities calculated. I can put it here. Now then I need to use either 1 or 2 or 4 probabilities to generate this kind of chance. Okay, basically I do not need to use all four probabilities at all. I use only any two at my job is done. Okay, that I will show. Okay, so to start with, first to place the first element, because this will be first order macro process. That is already known. With first unit is A, what is the probability of next unit? That means the second unit is depending on the first unit. So the first order macro process. Clear? So I have to put the first element. You can approach any of this method. Randomly you put it, or put depending on the composition also. The first element you have to put without using any probability. That is some sort of initialization. Then second unit onwards, you have to apply those probability. Okay. So calculation is done. We go to the actual logical part where you need to use that probability to generate the set. So let's say the first element is A. What is the probability of having AA? So generate random number and compare with PAA. This PAA actually the probability of AA sequence. Okay. If this is satisfied, next element is A. Okay. I do not need to use the PAB probability at all. Since I have only two possibilities, only one probability is sufficient. Now, if the first element is not A or this condition is not satisfied, then the next element is B. It's clear? So either you will get AA or you can get AB. Accordingly, you can store the element and keep adding these elements respective to the sum array root, sum A or sum B. So I have first element if it is A, I generate a random number compared with probability this. If it is satisfied, then I will say next element is A. If it is not, next is B. That's all. And store this information. One cycle is over. Go to the next cycle, assuming that first element is B. The same exercise, generate a random number, compare with P, B, B. So if the first element is B, next element will be either A or either B. Either it will be A sequence or B sequence. So I'm comparing with this. If it is satisfied, next element is B. If it is not satisfied, next element is A. And store this information and continue. So at the end, what you get? Sequence of this A, B, all these things. And you keep on counting how many A and how many B you have generated. Because you need to satisfy the condition given at the beginning. The unit copolymer with 10% B or 20% B. So at the end, you have to justify or check that criteria whether your accumulated number of B, which is in B, is matching with the set parameters. If it is not, we have to restart. Okay. And at the end, you may expect a sequence like this. If we are expressing A and B units in terms of integer 1, 2, the sequence will be like this. If it is in terms of AB, then something like this. Depends on your choice, which one you want. Okay, it's clear, at least to some extent, the application of first order Markov process. Okay, this is energy distribution. I will get back to this part again. Okay, before we get into the metropolis something. Now, system has a inherent probability, inherent tendency to come to the low energy state. You know that? Suppose I put some molecule at high energy state. So over the time, I may expect that it will come down to E0. Because we know that system has an inherent tendency to go towards low energy state. So after some time, I may expect that everything will be here. Isn't it? If everything is at E0, lowest energy states, then this is invalid. I am talking about a finite temperature, not 0 Kelvin. Okay, not 0 Kelvin. Maybe at room temperature. If everybody is coming to the low energy state, then this is invalid. I would say only one point or one line only. But it never happens, right? That means that every state or every energy state, every molecule is coming towards low energy state is not really true. There is a possibility that this path can be operated. That means a molecule from low energy state can move towards high energy state as well. Only under this condition, I can have a distribution of energy from low to high. It's clear? There is a tendency, does not mean that everybody will go to that low energy state. Tendency means possibility is there, but the reverse possibility cannot be ignored. Okay, this is the basis of metabolism. We started with this, then of course it will go further. Up to this one is clear. So what is that possibilities? Which one I place? Okay. Okay. So here is the metabolic scale. If there is a possibility, let us formulate it. So case 1, let us say I have two different energy states, EI and EF. EI is the lower, EF is the higher. Initial and final. Assume that EI is the lower level, EF is the higher level. Now, if EF is lower than EI, then according to our previous understanding, this transition will take place. Is clear? If it is greater than, then there is a probability of this transition. This probability is not zero. That's a finite probability. And what is that probability is here? Exponential minus delta E upon KB. What is the unit of this? So it is unitless. Okay. So then you get a probability. This delta E essentially the difference between this energy level, EF minus EI. If I know the values of EF minus EI, I can calculate delta E. If I know the temperature and KB is constant, I can estimate the probability. Okay. Then you generate a random number. If this random number is less than this probability, that is within this probability range, you move to the final energy states of EF, otherwise stable. This is the essence of Metropolis sampling or Metropolis Monte Carlo. But there's something behind it. I mean, what is the more theoretical basis behind this equation? That we need to little understand before we go further. Okay, there are three graphs I have shown. Maybe one or two will be reversible, other one will be irreversible. Can you tell me which this is reversible or irreversible? First one. Huh? Second one. Irreversible or non-reversible. That is an anonymous answer. Everybody agrees. The confusion comes between 1 and 3. Irreversible. What about 1? Okay. So how many things that third one is not reversible? Raise your hand. Supposed to be assumed to be everybody agree. What about the first one? I'll come back each of them. Reversible, irreversible. Anybody is thinking first one is reversible? No one. Reversible. Okay. Anybody? I got only one. Reversible. Anybody? 2 and 3 out of those 20 or 25. So why it is reversible? Can anybody? Yeah. Do you agree with this argument? What is saying that the system starts from somewhere, initial point, it travel and return to the point from where it started. That is the reason it is reversible. Okay. I give a different name without getting into the state and point. Okay. The detailed discussion over here. This is no doubt irreversible. Forget about it. Both are reversible, but from a different perspective. This is the reversibility that we study in thermodynamics, classical thermodynamics. Right? At every point it is reversible. Either you follow forward or reverse, doesn't matter. Every point it is reversible. That is called microscopic reversibility. Okay. This is also reversible. This is macroscopic reversibility. Okay. So if I now take a let either time scale or length scale, anything doesn't matter. If my length scale is up to this, quite large, then it's reversible. I do not see any irreversibility. But the moment I come into this domain, I see the forward and reverse path gives to different y value. This one not reversible. Yeah. So macroscopically it is reversible, but microscopically it is not. And this is both. Understood? And this kind of process has a hysteresis loop. There are many processes. Crystallization, melting, adsorption, desorption have shown this kind of hysteresis group. Okay, we understood the difference between these three. Let us see which one Metropolis is going to use or okay, or Metropolis is based on which one of them. Definitely not on this. Either this or this. This is called principles of detailed balance. I mean the concept is this, but essentially referring to the figure number 3. Okay, so probability of this is already known. I discussed. I have to derive this equation. The final form of the metabolism. Let us say I have a system, initial state I, energy level EI. Then probability of sampling of this particular state is given by n of I, which represents the probability density of state. So the overall probability from initial to final has 3 different probabilities. Try to understand the 3 different probabilities. I mentioned this buying fruits or vegetables. Now recall them. What are the 3 different steps? One is this Ni actually the probability of having that particular energy states. Okay, this is transition probability, which is almost invariant, and this is the final acceptance. Similar to your shopping criteria in fruit shop or vegetable shop. What do? The fruit must be present there, right? With your preset criteria. Then you have your own criteria that may be similar to a transition probability. And finally, you accept this. Clear? There are 3 different probabilities which gives the ultimate probability of the forward path. Having this energy level to sample that particular energy state, then a transition probability from I to A, and final acceptance. Okay, so if I now took the reverse one also, I should have these 3 different probabilities. Of course, the direction is reverse. One is NF, similar to NI, then transition probability of final to initial, and then acceptance. Okay, so I have forward path and reverse path. In 2 paths, I have 2 different probabilities. If I addressing this picture, then I can equate these two. Yes or no? Because at every point, this forward and reverse is equal, right? So I can equal these two based on this microscopic reversibility. Now let us see what happens. This is the forward path. This is the reverse one. I've equated. Now I'm just trying to rearrange them. I took this acceptance criteria, acceptance probability, I to F divided by F to I, and all other terms I have shift to right hand side. NF by Ni multiplied by 2 transition matrix. Typically, this is a symmetric matrix. So ratio is 1. Whether it F to I or I to F, there gives the same value for a symmetric matrix. So this goes away. So I have the ratio of NF by Ni. If I want to represent by Boltzmann probability, I can express NF by e to the power minus EF by kbt and Ni by e to the power minus EI by kbt. If we simplify this, I get this one. So this ratio, essentially this one, and this is the effective probability from I to F, which is nothing but the ratio of these two. This is what Metropolis has already suggested. Couple of slides back I have said. Clear? So we get back Metropolis criteria or sampling criteria, but the inherent physics and inherent science is this. Okay. The reason another reason behind showing all these things is this picture and this entire derivation is that whenever you are using Metropolis sampling, Metropolis Monte Carlo, remember that you have started with microscopic reversibility as the fundamental guiding lens. Okay, so you are going to simulate only an equilibrium system. If anything is non-equilibrium, far away from equilibrium, then do not try to apply metabolism. You may get wrong results. Yeah, up to this part. Okay, I think another definition is there, ergodicity. Anybody is familiar? So it says every accessible point in a configuration space can be reached in a finite number of MC steps. So basically it shows that if the system is ergodic, you can access entire energy space. Sometimes you might have learned this local minimum that is trapping somewhere, right? If you are trapped some space, hence you are not able to access that, or rest of the part you are not accessible. That is not ergodic. Okay, this is non-ergodic system. So metabolic sampling scheme applicable for ergodic system. That means if somewhere it's trapping, that may lead to a non-equilibrium system as well, where metabolic sampling will fail. Clear? Non-ergodic means suppose this part is non-accessible. That is non-ergodic. I cannot reach this point. But if I reach this point, I cannot come out. That is this trapping part. What you say local minimum. If your system has this kind of possibility, then application of Monte Carlo will be difficult. That nobody knows. You have to try, you have to give it and try. Some sort of local minimum. Some sort of local minimum. Where you get that. Then you apply so many other advanced sampling to get out of this local minimum. Umbrella sampling, weighted histogram analysis method, many things are there. They help you to get out of this local minimum or topic. Okay. Okay, this is potential energy function, some sort of getting into the actual modeling and simulation. How do I simulate a system? First, I have to model. How do I model? Model is basically interaction between molecules, which is governed by potential energy function. Are you familiar of any kind of potential energy function? One is Lennard-Jones. Any other? Any other potential energy function? Parallel, Hertzsprung, many. A long list, but most widely used is the Lennard-Jones. Sometimes Hertzsprung. Okay, and then some introduction to the ensemble. I think not introduction in this. Okay. Yeah, small introduction to ensemble and how many ensembles that we deal with. Okay, the next couple of slides. How do I simulate Monte Carlo simulation across this ensemble? Okay. How much time do I have now? 15-20 minutes? Huh? Okay. I think I'll be able to finish. Okay. So this is the typical representation of your energy potential. U of R proportional to 1 by R to the power. So any kind of potential as a function that you have, it follows this kind of inverse relationship. That means if you increase the distance, the value decreases. Right? The lowest value of this m is 1. What is the name of that potential? You know this. U of R proportional to 1 by R. What is the potential? Yes. That is the strongest potential, and Lj could be the weakest one. Okay. Okay. So ensemble definition here. Probability distribution for the state of the system commonly used. So basically, if I split this word, energy, the En from energy, and this SEM will form ensemble. It basically shows that you have an ensemble of energy store. That is essentially ensemble. And there are different types of ensembles that we use. Okay, I think one ensemble I have mentioned here. I think it is no longer being used. This was proposed long back, but hardly this ensemble is used. NVT is most widely used, then NPT, isobaric isothermal, then you have grand canonical UVT and Gibbs ensemble UVT. We'll get into that one after another. But what is the origin of these 3 parameters? This means for that particular ensemble, your N, V, and T will be constant. N is the number of molecules, V is the volume, T is the temperature. The origin, if you wish to know, I don't know whether I do not have that slide here, but go back to the definition of chemical potential. Can you recall? What is that? Mathematical expression of chemical potential. Del G by del Ni. Then outside some constant level. Do not want to use them, but anyway, let us try. Something is there, no? What is that? Okay. How many parameters you are keeping constant to define chemical potential? How many parameters you are keeping constant or fixing them to define chemical potential? 1, 2, or 3, or 4? How many? Okay. This is the origin of this definition of chemical that ensemble. So to define a system, you need these 3 parameters to fix. Otherwise, you can neither less than 3 nor more than 3. Less than 3 you cannot define. More than 3 you can not need it. Is it cover periodic boundary conditions? No, periodic DFT is done, no? So then PVC is done. Then. Okay, I will go through it simply without much detail. So as I mentioned, molecular simulation, both MC and MD, they are basically to deal with finite system. Okay. Till now, we do not have any supercomputer to simulate one mole of any substance. How many molecules are there in one mole? Roughly in the scale of 10 to the power 24, right? If you take only 2 molecules also, or binary interactions, right? Simple binary interactions. For one set of calculations, the total number of calculations will be 10 to the power 48. Clear or not? It is n square, right? NC2 scales with n square. So difficult to calculate. So what we do is much lower than 10 to the power 24. Sometimes 10 to the power 3, few thousands, 4, 5, 6, 7, at max 8 or 10. I have not seen anything beyond that. Total number of molecules 10 to the power 10 and beyond, difficult to see. Okay. Now, if I take that smaller number and still I am predicting the properties at the bulk level, that level which I can measure, then how it is possible? I'm getting the point. I'm taking a maybe 10 to the power 8, let's example. But 1 mole is 10 to the power 24. Right? 3 times down the line. Still I'm able to match the data. That is because of the application of periodic boundary conditions. So let me elaborate from practical point of view, then I'll get back to you. So in real experiment, let us say we have a liquid sample, we prepare 100 ml, 10 ml, right? Then you go to different characterization, right? Microscope, DSC, TG, so many things, right? Do you take all 100 ml for each characterization? How much you take? Sometimes microliter. Am I right? If you take a solid sample, let's say thin film you prepare, maybe 5 centimeter by 5 centimeter, 25 centimeter square, and you want to do the microscope study. Maybe optical microscope. How much do you take? Inside 25 square. Sometimes micron, sometimes in the scale of millimeter also. Otherwise, in the scale of micron. And you claim that both liquid and solid sample, whatever the properties I am getting with this tiny sample, it represents the entire sample. Is it not an assumption? We assume that, right? We can apply the same criteria over here also. Right? So we take a small simulation box. Then we need to replicate infinite number of times. Then we claim that whatever we see in this small box, it represents the bulk system or infinite system. Okay, this is the logic behind periodic boundary condition. And the way we do it, this application of these two equations. So while you simulate, you are allowed to, particles can move outside the box also without any problem. This is maybe your simulation box. Particle is over here, you allow them to move anywhere they wish. Okay. But you keep track their position, keeping this as the reference. Every time they're going out, reassign their coordinate somewhere here. If they're going out, one image of this particular will enter from the back, so that your number of the molecules will be preserved. In this way, what you are doing actually, you are removing this boundary. It's clear. If something is going out and someone is coming in, that means there is practically no boundary. So you are essentially simulating a bulk system. Clear? So to do that, you can use any of these equations. This is your final positions. This is initial. Initial means somewhere outside the box. Final means inside the box, because this is the range that is accessible to you, not beyond this. And this is length of the box, integer of x by l. You can apply them, you can get back here. This is for positive coordinates. This is for negative coordinates. Okay. So every time you take a move or you just going out, next position, you check whether it is outside the box or not. If it is, bring it back to your control box. If you keep on doing that, you are accessing actually entire thing without much boundary effect. So in reality, you are doing the bulk simulation, even though your system is quite small. Okay, it's clear. Now you can ask the questions. Can I do that with number of particles with 10 or even 1 or 2? Since I am replicating my simulation box infinite number of times, I can take my system as small as I can. Very tiny box and 1 or 2 number of molecules. Can I do that? I want to simulate a system. Let's say I simulate liquid water. Right? I learn periodic boundary conditions. This was that you take a smaller system, replicate infinite times using this equation, you will be able to simulate bulk. Right? I take a very tiny system, tiny box, and using one number of molecules, either 1, 2, or maximum 10. Am I going to represent the bulk properties? Right? That means this is wrong. Are you able to get the question? Even though this is fine, powerful technique, does not mean that you can play with 10 is to 10 or 1 or 2. If you do that, you will get a finite size of it. Okay. So for a new system, to decide what n you can take, you have to try with couple of such system sizes. Okay. Then you have to plot system size n versus certain properties and see after which it is stabilized. Something like this. You can have some properties x, y, whatever case may be, it is number of particles, and either it may extend this kind of line or this kind of line. Okay, either it can increase and steady or it can decrease and steady. Then you can claim that if I take n up to this point, I'm able to simulate bulk. If you take somewhere here, you are not going to represent bulk, even though you are using periodic boundary condition. Clear? Okay. Next couple of slides, how to carry out MC simulation in various ensembles. That 4 or 5 ensembles are next one. Before I get into that, I need to answer this question. What do I mean by simulation? What exactly we simulate? Can anybody try to answer this?
Processes that are not possible at bulk scale, at molecular level, something is changing, or like very high pressure that we cannot perform in laboratory setting, that we can simulate.
Anything else? This is not the answer that I'm looking. I'm looking for more fundamental problem. I'm giving the hint. What exactly we do in simulation? Step. More fundamental problem. What exactly we do? And rest of the things is nothing but the outcome of that. Replicate. That is a more fundamental. Right. Okay. Getting that? So, I look like a team of atoms. Then you get successful. More fundamental property. This will be derived from the time. Not satisfied. There are more fundamental properties that we do. Whether it is written somewhere or not, that I do not know. But the moment we go further, you will perhaps will agree. Okay. So let me give an example, then I will try to justify the answer. Suppose you have a water vapor at 100 degrees centigrade. You keep on cooling it down, keeping pressure constant. At what temperature it will form liquid? You will see liquefaction condensation. Why it will condense? Water vapor may be more than 100 degrees centigrade. Keep on cooling it down. You will see water droplet formation. Yes or no? Yes. At which temperature you will see that vapor comes to liquid water? Below 100. You keep on decreasing temperature. Then entire water will liquefy. Clear? You keep on decreasing further. Negative temperature. Regular. Solid vapor. What happened to the system? You have done only decreasing temperature, right? What happened to the system, to the molecule water? Entropy. बहुत बड़ा term हो रहा है. There are more fundamental properties. Now, density will macroscopic properties. हाँ? आओ थोड़ा पीछे जाओ. You will get one more term. Random motion or Brownian motion. Molecules velocity. Kinetic energy. I think this is the most fundamental property. Correct? The moment you decrease temperature, what is the first property of the molecule got affected? Very correct. And remaining is the outcome of it. Correct or not? So what you do in simulation exactly to mimic that. And may not be in the form of kinetic energy in Monte Carlo simulation. In MDS, you do kinetic energy. In MC, kinetic energy has no role to play. Everything is potential energy. But essentially, what to simulate is that random motion, which may be a function of temperature, pressure, and many other parameters. Okay, clear? I can go from one phase to another phase if I can manipulate this randomness. Right? The way I have done by changing temperature from vapor to liquid, I have decreased the randomness. Velocity decreases, right? That what is called free fall, right? Mean free fall. With a much higher in gas phase or vapor phase, much less in liquid, even much less in solid. So what I have done, I just manipulate the velocity indirectly, because the velocity of kinetic energy linked with the temperature, thermal energy. What is that equation that correct? That is a very famous equation. Half mv square is equal to half kt. What is that? Equipartition principle or something. Right? Half mv square to half kt. Right? So in simulation, whether it is MC or MD, what essentially we do is to keep track of this particle's motion or random motion. That is exactly nothing else. Rest of the thing that we see, we observe is outcome of this. Okay. Now, how do I do this randomization or random motion for the different positions? In MD, that is by Newtonian dynamics. In MC, something different. Not Newtonian dynamics. It is called Monte Carlo move. Randomly, you assign that I have a position somewhere here. This is my one positions, X, Y, Z. Randomly, I ask this molecule to go here or try to go there. This may be initial position, this is my final position. With a certain criteria that I to go there. And then apply metropolis criteria whether I'm to accept this or not. This particular method that I am describing is known as Monte Carlo move. It's clear? With this method, you can mimic that random motion which is present in the system. Clear? This is exactly what you do in simulation. Nothing beyond that. And if you can manipulate this random motion, you can get whatever properties that you want. Okay. Okay, the first one is NVT ensemble, 2 lines of pseudo code. Are you familiar with this? Code and pseudo code. Anybody familiar or nobody? Code is specific to a specific programming language. C, Fortran, Python, etc. Pseudo code is not specific to any language. It's just the description of the logic or algorithm. Language independent. If you can understand the pseudo code logic, then anybody can write the code respect to their preferred languages. That is called pseudo. Okay. So we want to simulate system using NVT ensemble. What is the procedure protocol that I need to follow? Okay. Since it is NVT, I need to fix these 3 parameters at the beginning. Okay. Number of molecules, length of the box, the volume is L cube, that is constant, and keep the temperature constant. Okay. And then what I have shown, try to show here is jumping from one place to another place. I have to define a range of that. It cannot be minus infinity to plus infinity. Right? That range is defined here. Some sort of minus R to plus R. Okay? Clear? Not beyond this value. So you are allowed to take the new position. You can allow to jump to the new position, but the new position will be bounded by this boundary. Not beyond this. Okay? And then you have initial coordinates. You have stored somewhere. You can read the initial coordinates. I hope everybody is familiar with that. Reading from the file. Then initiate a loop of number of Monte Carlo steps. How many Monte Carlo steps you want to simulate? Let me define what is Monte Carlo steps. It is here. One Monte Carlo step is number of Monte Carlo move per Monte Carlo step. That means if I have 100 number of molecules in one iteration, if I allow 100 number of steps, 100 number of possible movement, that means one possible move to each molecule. Clear? That is one Monte Carlo step. That within one Monte Carlo step, I have allowed every molecule to move once. Whether they can move or not, that is different also. That will be subject to certain terms and conditions. If metropolis sampling says that no, you are not allowed to move, that molecule has to stay back. But the molecule got an opportunity that can take the move. That is one Monte Carlo step. Okay. Okay. Then to start this simulation, you have to pick up randomly one molecule out of n that you can do here. Look at this definition I had mentioned in the pi calculation slide. And since this is non-integer, some language may not accept straightforward way. So you have to convert the category or the type of the variable. Right? But some language may directly accept this. So the value will come from 0 to n minus 1. The moment you get mth molecule, you can get the initial coordinate of that. Something like this. This is my initial position. Okay. Then from delta x, this range, you get a random value across x, y, and z. Okay. So this is known to me x, I, y, I, z, I. Then I allow delta x, delta y, delta z across 3 different directions. I get the new position x, f, y, f, and z. This delta x, delta y, delta z has been chosen from this range randomly. Something can be from minus, something can be from plus. It can be 0 also. It can be 0 because this entire range including 0. So any value from this range it can take up. Okay. So that gives me the final positions. So I have initial positions, I have final positions. Now I can calculate Metropolis criteria. Clear? So what you need to do is to get the energy of each of these step, EI and EF, then apply Metropolis criteria, whether it is satisfying or not. Okay, clear? But before you go that, there are a couple of checkpoint is there. Checkpoint in the sense that the moment you are asking this molecule to jump over here, you need to check whether this is available or not. That means you need to avoid overlapping. Okay, suppose a molecule already sitting here, somewhere here, already existing. You cannot occupy this position by anyone. Okay, so the moment you pick up this final coordinate x, y, and z, to check whether this position is available or not. Basically, position from this particle to the rest of the particles. That is perhaps given somewhere here. Mth particle J goes to 1 to n. If it is less than sigma or molecular diameter, that means there is significant overlap. Clear? The distance between two molecules should not be less than 1 molecular diameter. It has to be beyond that. That you have to initialize somewhere at the beginning. You know, if I have not mentioned here, everything comes at the initialization. And if it is not, you can proceed further. Clear? Then based on your initial coordinate, position is known. If the position is known, you can calculate interparticle distance, intermolecular distance, Rij. You have already defined potential energy function. You can calculate both EI and EF since final position is known to you. If I know this, I can calculate delta E. I can calculate probability, and then I can apply the Metropolis criteria. If it is satisfied, I will accept the final position. If it is not, stay back at the initial position. Clear? If it is accepted, then you have to update this coordinate position. If it is not, do nothing. Clear? This entire exercise that I have narrated is one Monte Carlo move. Okay, so you have to repeat n times of this move for one Monte Carlo step. If you have 1000 particles, this loop will rotate 1000 times. Okay, that means, are you sure? Are you confident that all 1000 particles or molecules will get one opportunity to move? Why not? Theoretically, yes. Practically, not. Okay, so there is a possibility that in a given Monte Carlo state, you are giving opportunity, but since you are picking up this mth molecule randomly, there is a possibility that one molecule is picking up more than once. Someone else is not getting the chance. Right? There is possibility. And it happens actually. You can check it. That means we are doing something wrong. In one Monte Carlo state, suppose I have 1000 particles, it happens that 10 particles did not get a chance to move. I mean, they have not picked up this mth one that you see, we randomly picked up. No, some 10 particles did not get a chance. Are you doing anything wrong? No. No, they are not selected at all. Forget about the jumping. That means, let me go back. This step, this M that was selected randomly, out of 1000, this some 10 particles did not get a chance at all. That means something is wrong. Isn't it? Apparently, it looks that something is wrong. Right? Now, the solution is that you are not simulating for only one Monte Carlo step. You are simulating millions of Monte Carlo steps. So this error will nullify as you increase the number of Monte Carlo steps. Clear? Initial structure. What position? Initial or final? Then you have to ask the question, how are getting initial position? Okay, that I think I did not keep the slide here. Initial position you need to generate by your own.
For each and every molecule.
Yes,
Is it different?
that depends on you. The way you want to generate. Okay, so I can give you one such protocol here. Let's say I have this box. Okay, you know how many number of molecules you want to accommodate, subject to n by the row density. You should not try to accommodate more number of molecules with that limited box. Okay, then what you can do is randomly place them. Randomly pick up the coordinate.
Greater than density and then place them.
So you pick up a coordinate, assign a particle to that coordinate. Clear? Coordinate picking up already we learned in pi calculation and Monte Carlo integration. But this method has a problem. For a dilute system, it may work well. For little bit concentrated system, every time you pick up a point, you need to check whether anybody is nearby or not. Isn't it? Understood? For a very dilute system, this possibility is very less. Otherwise, it is a serious issue. Okay, so get out of this. The simplest method is you keep on adding molecule not randomly, sequencing. I put one here, I know the coordinates here. Manual I can do it. Excel sheet can do it for you. Okay, then I give a distance of sigma, I put another one and keep on doing it. No, only n. That is the n. Density already fixed before n. So I may be able to fill something like this. Completely filled. Okay, so this may represent my initial structure, which is hypothetical, not representing an acceptable structure for the simulation. Okay, clear? Then you have already decided this is my Monte Carlo algorithm that I'm going to use. To start from this, apply your algorithm, you will get randomly distributed system. From that, your actual simulation will start. It's clear? You can follow either of these approach. You can follow this random placement one as more time taking, more laborious. Better to use sequential method. I know how many number of molecules I am place. I know the box size. Right? I know the diameter of the molecules. I can sequentially put it one after another, and Microsoft Excel can do it for you. Okay, set that coordinate, start your simulation, then apply your simulation algorithm. You come down to here. This may be equivalent to your equilibration text. You need to equilibrate, right? Are you familiar? Equilibration. Equilibration. Then in real experiment, you want to study some parameters. What you do? Let's say I want to study some properties as a function of temperature. I change the temperature from 25 to 30. I do not take the data immediately. Right? I wait for some time. What is that something? Some system should be so-called steady. Temperature should be steady at 30 degrees. Right? That time it's equilibration time. Okay. So before you do the simulation, basically you have to erase the previous history. That is what equilibration is. Okay. Any other questions? NVT ensemble. It's clear. Details perhaps you will learn in your hands-on. Am I right, Anand? Okay. This is some brief outline. Details you will see. Similar to this approach when you follow the hands-on system. Okay. Let's move to the next ensemble, NPT, where number of molecules will be constant, number of temperature and pressure has to be very constant. Now in Monte Carlo simulation, we do not calculate pressure. There is an assumption behind it. We have to go with that. When pressure is keeping constant, T also constant, so we allow volume to fluctuate. This is the protocol used in NPT ensemble, Monte Carlo. But in MT, you can actually calculate pressure from the simulation. because pressure is linked with the kinetic energy, internal pressure. Since we are not dealing with any kind of velocity in Monte Carlo simulation, no kinetic energy, so we cannot calculate pressure from the Monte Carlo simulation. Clear? So we have to use some sort of a indirect part, and to keep volume pressure constant, let volume to fluctuate. And this is the schematic diagram that I have shown here in both the sides. Assume that this red color box is your simulation box, allowed to fluctuate with one which is inner one. This is maybe contraction, outer blue one will be the expansion. Okay, so with a certain range of volume, not infinite, not anywhere everywhere, we allow that say 20% volume can fluctuate. The initial volume is V plus minus 20%. Within that, let it fluctuate. Okay? So the protocol will be whatever I have seen in NVT ensemble, that was typically displacement move. Okay, this kind of move, displacement. This move will be associated with pressure changing or volume changing. Here. So how to execute the volume change move? Displacement already we have discussed. So I have initial volume. This is the final volume, that is plus delta V. This delta V is decided from the range, minus delta V to plus delta V. Okay, any value it can pick up, like minus delta X to plus delta X. If it is negative, it is contraction. If it is positive, it is expansion. But within this boundary that you have decided, so you get final volume here. From that final volume, calculate final box size. From final box size, you can calculate the position of the particles. Okay, and then apply this equation to calculate the probability. Now you can see that because of this volume change, I have two additional terms, second and third, in addition to this first one. This is the first one and the previous one. Additional term is referring to the volume change. Okay, in a particular move, if there is no volume change, second term goes to 0. VF is equal to VA. Third term, VF by VA equal to 1. ln1 is 0. So equation is correct. Okay, so apply this and then continue the simulation. The protocol is typically in one Monte Carlo steps to try to attempt one volume change move. This standard protocol, but you can change it required. Okay, that means your random number generator that you have generated for picking up mth molecule, the range will be now up to n plus 1. Okay, and this volume change moves will be decided randomly, not like I'll complete n number of displacement, then one volume change. No, the volume change move can come at any time. Okay, on average, one volume change per Monte Carlo step. Okay, similar to the previous discussion, it may happen that in one Monte Carlo steps, more than one volume change you have performed. In some Monte Carlo steps, 0. But overall, you to calculate, you will have almost one volume change over a Monte Carlo step. Okay. This is the details of volume change move. Displacement already we have discussed. I don't need to repeat that again. Okay. So you have final volume based on this initial plus delta V, then final box size VF to the power 1/3. Then you have to rescale the coordinates. So if I now go back to that schematic, now look at it. Suppose initially this position was here. Red cross you can observe with respect to red color box. Now suppose I have contracted this box. Now box is here, particle is outside the box. Not acceptable. So I have to transfer or translate this coordinate into this box. So I have to rescale the coordinate. Clear? That is done with this equation. XF, XI with the initial position into LF by LF. I know Li, I know LF, I can rescale the coordinate. The moment I rescale the coordinates, the intermolecular distance also will change. Clear? So I have to recalculate EI and EA based on the initial position and final position. Then calculate the probability that I have shown the equation and apply the metropolis criteria to accept everything. Clear? Details will be, more details will be done in answer test. Okay. You may not be able to see these equations there. I don't know this equation will be shown or not. You are not going to show this equation, right? So whatever you show the application, the machines behind the application is this. This is the way they are going to work, which are not visible from the outside. We are talking about random number generator. That is system predefined.
Yes.
Any programming language, you have random number generator. Call that, you give the random.
Yes, so if it is the function, the way it is generating a random number, if it is following an algorithm, that really be random.
Okay, that is very good question. Most of the cases they are known as pseudo random numbers. I mentioned briefly in the beginning, they are unbiased and not 100% unbiased. Some biasing is there, but not good. If you want to learn more, then you have to read a book. That author is, I think, Noot. Write the name of the author. NUH. Book is Art of Computer Programming, Volume 2. You will find a huge section on random number. No, few slides. Okay. So if you want to learn how this random number generator works, you can read that chapter. There are so many methods people use, and this is also an area of research. Okay, if you use a wrong random number generator, do not expect good result. That I have learned during my PhD. Okay. Okay, so this is done. NPT ensemble. Okay. Let's move to the third one. NUVT. Grand canonical ensemble. This is the definition of chemical potential. Now, when you are keeping chemical potential constant, the N is supposed to be variable, right? In the first two ensemble, we keep N constant. Now, N has to be variable. How can I make N variable? I have to follow this protocol. This particle can in, particle can get out of the simulation box. Okay, that means I can have insertion of particle into the simulation box, deletion of the particle from the simulation box, so that I can capture this part. Del Ni. Del Ni can be positive, can be negative. Clear? So in addition to this displacement, if I implement these two, I will mimic mu VDS. Yeah, provided I know the value of chemical potential. Okay, so I'm not going to discuss how to calculate chemical potential, otherwise it will take a long time. But I will mention the method. Freedom particle insertion method. One you can study. That is a method based on which you can calculate chemical potential if it is not known to you. Okay, so now I have three different possibilities: displacement, insertion, and deletion. You can approach either one, because the moment I have three different possibilities, I have to give some kind of ratio to them. Okay, either 1:1:1 or 2:1:1. Both the methods are equally accurate. I mean, many people have used equal probability to all three possible moves. Some people have given more probability to the displacement over the insertion and deletion. Okay, so now I have to choose each of these move. Displacement I do not need to discuss. It is exactly same as you. How am I going to implement insertion or deletion? Okay, what should be the logic? So I have n number of system particles. I am to add one more into the system. What should be the logic? What steps? You want to accommodate one more particle. I need to ensure that one chair is empty, is available, right? So first you need to find out the coordinates. Clear? X, Y, Z, and check whether it is available or not. If there is empty chair, I can invite a new student. Otherwise, I will say no. Okay. So first we check this. If it is available, then put it back. And then calculate initial energy based on n number of system, final energy based on n plus 1 number of system. And then calculate the probability, follow metabolist criteria, take the data. Simple. What about deletion? Much easier. You need to just remove this particle from this box. So randomly select particle only, not coordinates. The way I have selected the particles in the displacement move, in the same way, you select a particle randomly and then you delete from the system. Now your initial energy will based on n number of system, final energy n minus 1 number of particles. Clear? You have EI, you have EF, you can calculate the probability, invite metropolis to take the decision. It's clear? This is written over here. This is the probability for displacement. This is the probability for insertion. And this is for deletion. Okay. And details are over here. What I had discussed previously, the same is written over here in the simple one. One thing that you be very careful if you are writing your own code, the problem you will face the moment to add a new element over here, particle size numbers goes from n to n plus 1. You have predefined your array to hold the particles with certain size. Right? Say 1000 particles. Now it is 1000 plus 1. Whether your array will accommodate. Immediately it will go wrong, right? So what to do? There are two approaches. One is you follow a little bit, advanced programming like dynamic memory allocation or linked list. Those who are not comfortable follow the last one. Okay, 1.5 times n or 2 times of n array size you define a array. There are 1000 particles. I will define an array size of 2000. So this much memory already have available, and particle size will never pass 2000. Okay, the moment you add a new particle, you can easily accommodate. What will happen if you delete a particle? That will be a little bit tricky. So I have this list. This is the typical way to represent array, right? To learn long back. Suppose this box particle sitting here is going out. Then this array will be continuous, I believe. It should not be discontinuous.
Shift,
Yes. Yes. The moment this is empty and this move accepted, deletion move, it accepted, this is empty, then each of them should move one step ahead so that the last will be empty. This additional work they have to do, but your software is already taken care of. All these things is inbuilt, but you should know the way they work. Okay. Only position. Only position.
Not the sigma, like the molecular dynamics.
Sigma that already defined. It is.
It's constant for each.
Yes, if it is the only one molecular system, there will be only one sigma for everybody. If it is
Position is
only position. For MG, it is position plus velocity. For MC, only position. Okay.
Insertion part.
Insertion part.
Previous. That you said the insertion move that I first we select the coordinate and then check whether there is space.
Whether that coordinate is available or not.
And then only directly.
Then only you can add the particle. Okay. This is what I have discussed. Whether it is n plus 1 or n minus 1. Okay. So I think this is the final one. Next is mu PT. This ensemble. This might be more realistic ensemble. If we are dealing with, let's say, paper level equilibria, 2-phase equilibria, typically we carry out experiment in under constant pressure and temperature. Okay. And this diagram shows this existence of two phases. Okay. Now it is pressure constant. Then according to our NPT formalism, we can allow volume to fluctuate. NPT ensemble we have learned volume change move. Okay, now follow this schematic. I have phase A over here and phase B over here. Two phases. Now the molecule can go from here to here. Right? Since it is under equilibrium, this same molecule can come down here also. So this is here, this path B. So we need to find out how many different possibilities of such kind of moves we can have. One is displacement. It is here in both the phases. Second is this molecule can go up and down. That means molecule from phase 1 can go to phase 2. Liquid to vapor, vapor to liquid. That is particle transfer, this B. Okay. Then there is C. which is related to the volume change. Because I am keeping pressure constant, so I have to ensure that volume is fluctuating. So there are two different approaches that we will follow. One is keeping total volume constant, allowing this individual volume to fluctuate. Clear? That can be done by, this is the phase boundary, horizontal black line. If I move up and down, this is basically implementing or mimicking volume change. Maybe the volume change decreasing the top, increasing the bottom, or the other way. Okay. Other approach is allow the entire volume to fluctuate. This and this both will fluctuate. Clear? That means total volume does not remain constant. That is a little bit tricky. Most of the cases we follow the first one. We keep total volume constant with these two phases, but allowing this individual volume to fluctuate. That is relatively easier to do. Okay, let me summarize. We have three different moves now. One is displacement, that is same as NVT displacement in the individual phases. Then the second one is particle transfer. That means liquid molecule can go to vapor phase, vapor can go to liquid. Third is the volume change. This phase boundary can move up and down, which represent either a volume expansion in the bottom, which is contraction at the top, or the reverse. Is clear? Three different possible moves. Doubt? Good.
So it will require two different randomization processes.
Yes.
Okay. Then there's the space boundary that is shifting the volume. So how do you shift this thing and then just let the postpone move, like the final equation of that?
No, they all three can expand.
But you said that's a tough one. So you just
That is a schematic representation. Okay, so I can allow these three blocks to expand. Then similarly, this will be contracted. The total volume remains constant. That means no. Let me write down somewhere here. So this is the volume, that is V1 plus V2. Okay, this will remain constant. I can have V1 plus delta V. I can have V2 minus delta V. Or the other way around. I can have plus minus here, minus plus here. In this way, I can change. Okay, so if the bottom one is expanding, equivalently top one will be contract. Or the other way. So the total volume remains constant. Adjacent coexistence. Okay, so this is the schematic representation of three different moves. Displacement already we have discussed. We don't need to repeat. Volume change already discussed. This will be same. Only thing is that in that NPT ensemble, only one box was involved. Here I have two different boxes. So if I am expanding box 1, I have to contract box 2. If I am expanding box 1, V1 plus delta V, I have to implement V2 minus delta V. So both the boxes I have to take it together. That means repetition of the same thing with different volume change. Same volume change mode that we discussed in NPT ensemble. This is not particle displacement, volume change. That is particle transfer. That is particle transfer.
Yes.
No, particle transfer is different move than volume change. Do not get confused. The independent mode. Okay. Displacement is clear. I think there is no doubt. I'll come to the individual move. Okay. Let us see which one coming first. This is the steps for selection of moves. Since I have a series of moves, I can give the relative probability for each of these moves. I can select which move I want to perform. Okay. This is volume change. Now this part I have done in NPT ensemble. Right? Only the first one. Now I have to take into the second one. Because if volume 1 is increasing, volume 2 has to decrease. So I have to get the L1, which is the length of the first box, and then coordinates in the first box. Then same thing I have to repeat for the second box. I have not written down here, but I have to write here. L2F is equal to P2F to answer. Get H2A for all the coordinate molecules in the second box. Then calculate overall energy. Okay. So I have two different boxes to join together. I have N1 and N2 molecules in box 1, box 2. When you're dealing with box 1, pay attention only N1 number of molecules. When you're dealing with box 2, pay attention to the N2 number of molecules only. Both displacement and volume change. Clear? Okay. Do not get confused that I have huge system. I have to take note. Clear? And then this is the final probability equation. Acceptance probability. Okay. Let me see there is volume change move. Then particle transfer. Particle transfer is essentially I am moving one particle from phase 1 to phase 2. What does it mean? I am deleting from phase 1, inserting to phase 2. So it's a combination of insert and deletion. Clear? What I discussed in the previous instance. Right? So then you start with either deletion or insertion, whichever case may be. But insertion is more difficult than deletion, isn't it? So you are trying to place a particle somewhere here. Let's say this is the box. You want to move from here to here, isn't it? The most difficult part is to get a vacancy over here, right? So first start with that. You look at a position over here where the particle will be inserted. If it is available, all the distance criteria satisfied, then select a molecule from here. Then delete this, add it over here. Is clear? So I am to delete from box 1 and add to box 2. Where I am going to add, that position I have to find out first. Okay, it may happen that there is no vacancy, that move rejected, no possibility. Then this is randomly picked up a position where the vacancy is not available. It is almost overlapping with the existing one. So this move is rejected. So first to pick up this point, available position. If it is available, then pick up a molecule from the other box. This molecule will shift to here. Clear? Then this box will be n is equal to n plus 1. This side will be n is equal to n minus 1. Okay. Accordingly, if the move is accepted, then you have to update the number of molecules following that insertion deletion move. Quite complicated, with time taking. If you are writing your own code, it will take time. Insertion also you have to manipulate this array. Deletion also you have to manipulate this array at the end. Clear? And this is the acceptance criteria for this move. Particle transfer. I think it's done. Okay. If still you have any questions. That will be within that box only. You cannot contact the molecule, you have to rescale the coordinates. If this is contracting, then you rescale the coordinate within this box only. And if it is expanding, rescale the coordinate within this box only. Then calculate energy over here, calculate energy over here.
Okay, so we again like to thank Dr. Carlo for the wonderful introduction in Monte Carlo simulation. And he is there in the department. You can always meet. He's in the ground floor of this building. You can always have a chat with him. He is accessible. So, as a token of gratitude, I like
You must
to
We're almost 12.
yeah, as a token of gratitude, I'd like to present a small memento for the wonderful. Thank you. So we break for tea.
Back.
Yeah.
Okay.
So we break for tea and maybe 15-20 minutes come back.
Okay.
You want to? Yeah.